for the unit Solutions, Dilute Solutions and Colligative Properties. In our previous lecture, we discussed osmotic pressure, reverse osmosis, theories of osmosis, measurement of osmotic pressure, applications of osmotic pressure and some examples related to osmotic pressure. In the continuation, today we are going to discuss relationship between osmotic pressure and vapor pressure, Wantoff's theory of dilute solutions, some examples related to Wantoff's theory. At first, we are going to discuss the relationship between osmotic pressure and vapor pressure. Let a dilute aqueous solution is filled in a capillary tube which is closed at one end with semi-permeable membrane. This filled capillary tube is placed in pure solvent and the entire apparatus is closed with a bell jar. At osmotic equilibrium, the bell jar is saturated with water vapor. At this point, the osmotic pressure will be equal to the hydrostatic pressure. Osmotic pressure pi is given as h into d into g. Here h is the height of the column, g is acceleration due to gravity and d is density of the solution. We have taken P naught B equal to vapor pressure of pure solvent and Ps equal to the vapor pressure of solution. At the level A, vapor pressure is equal to P naught B and at the level B, the vapor pressure is equal to Ps. Obviously, the vapor pressure at the level A is greater than the vapor pressure at the level B. Now, P naught B minus Ps is equal to h into capital D into g. Here capital D is the density of water vapor. Dividing equation 1 by equation 2, we get pi upon P naught B minus Ps equal to small d upon capital D. Here small d is the density of solution and capital D is the density of water vapor. As on constant temperature, the ratio of two densities is constant, hence we get pi is equal to constant into P naught B minus Ps. Therefore, pi is directly proportional to P naught B minus Ps, or we can say osmotic pressure is directly proportional to lowering in vapor pressure. As we know that P naught B into V equal to Nb into RT, this equation can be used if we consider water vapor as an ideal gas. Hence, P naught B into V will be equal to Wb upon Mb into RT. Therefore, P naught B into Mb will be equal to Wb upon V into RT, or we can say P naught B into Mb will be equal to capital D into RT, where capital D is the density of water vapor. Dividing equation 3 by 5, we get P naught B minus Ps upon P naught B equal to pi into capital D upon small d into Ma upon RT into capital D, or we can say delta P upon P naught B equal to pi into Ma upon small d into RT. As at a fixed temperature, Ma upon dRT is constant, therefore, delta P upon P naught B is directly proportional to pi, or we can say that relative lowering in vapor pressure is directly proportional to osmotic pressure. Now we are going to discuss Wantoff's laws for osmotic pressure. Wantoff, analyzing the data available for dilute solutions, concluded that the osmotic pressure of dilute solutions varied in the same way with temperature and concentration as the gases. He realized that there exists an analogy between the dilute solutions and the gases, provided the osmotic pressure is taken in place of gaseous pressure. On the basis of his conclusions, he gave some laws. Now we will discuss these laws one by one. First law is Boyles Wantoff Law. According to this law, osmotic pressure of a dilute solution is directly proportional to concentration, temperature remaining constant. The concentration of the solution containing 1 mole per liter will be given as 1 upon V. So, according to Boyles Wantoff Law, pi will be directly proportional to 1 upon V, or we can say that pi V is equal to constant. Wantoff presumed that the osmotic pressure of dilute solutions is due to the bombardment of solute particles against the semi-permeable membrane, as the gas pressure is due to the hits recorded against the wall of the container. Now we are going to discuss second Wantoff law, which is temperature pressure law or Charles Wantoff law. According to this law, concentration remaining constant, the osmotic pressure of the dilute solutions is directly proportional to their absolute temperature. We can say pi is directly proportional to T, or pi upon T is equal to constant. Combining the two laws, when concentration and osmotic pressure both are changing, pi is directly proportional to C into T. We have taken C equal to 1 upon V because we have taken concentration as 1 mole dissolved in V liters of solution. Hence, putting C equal to 1 upon V, we get pi equal to K into 1 upon V into T, or pi V is equal to St. Here S is called the molar solution constant. This equation can also be written as pi V is equal to RT, where R is molar gas constant. Here V is the volume of the solution in which 1 mole of the solute has been dissolved. T is the absolute temperature and pi is the osmotic pressure of the dilute solution. If n moles of the solute has been dissolved in V liters of the solution, then concentration will be equal to n upon V, and equation will become pi V equal to Nst, or pi V equal to nRT. Now we will discuss third law of Wantoff's theory. Equimolecular dilute solutions exert same osmotic pressure at same temperature. The solutions with same osmotic pressure are known as isotonic solutions or isosmotic solutions. This law is similar to Avogadro's hypothesis, which states that equal volumes of dilute solutions of different solutes having the same temperature and osmotic pressure contain equal number of molecules. For solution 1, if pi V is equal to N1 St, and for solution 2, if pi V equal to N2 St, then if osmotic pressure and temperature of both the solutions are same, then N1 will be equal to N2. The analogy of dilute solutions with gases is hence perfect. This led Wantoff to suggest that a solute in dissolved state behaves as a gas and the osmotic pressure of the solution is equal to the pressure which the solute would exert if it were a gas at the same temperature and occupying the same volume as that of the solution. This statement is known as Wantoff's law. We can determine the molecular masses if we have osmotic pressure data by using Wantoff's law, as we know that pi V is equal to Nst, and we also know that N is equal to W upon M. If Wa grams of the solute is dissolved in V liters of solution and molecular mass of the solute is Ma, then pi V will be equal to Wa upon Ma into St, or we can say that Ma will be equal to Wa into St upon pi V. Here Wa is the mass of the solute dissolved in V liters of solution exerting osmotic pressure equal to pi at absolute temperature T. Knowing all other values, molecular mass of the solute can be calculated. If we consider two solutions 1 and 2 having N1 and N2 moles of the solute in V1 and V2 volume respectively. Then pi 1 and pi 2 can be taken as their osmotic pressures at temperature T. Now from equation pi V equal to NST, for solution we have pi 1 V1 equal to N1 ST or pi 1 equal to N1 upon V1 ST. For solution 2, pi 2 V2 equal to N2 ST or pi 2 equal to N2 upon V2 ST. If both the solutions are isotonic, then pi 1 will be equal to pi 2. Therefore, N1 upon V1 ST will be equal to N2 upon V2 ST, or we can say N1 upon V1 equal to N2 upon V2. N1 can be taken as equal to W1 upon M1, hence W1 upon M1 V1 will be equal to W2 upon M2 V2. This is the condition for isotonic solutions. So, if we have two isotonic solutions and we know the molecular mass of a solute, the molecular mass of another solute can be determined without knowing their osmotic pressures. Now we are going to discuss some examples related to Wantoff's theory for better understanding of Wantoff's theory. A solution is prepared by dissolving 1.08 grams of human serum albumin, a protein from blood plasma, in 50 centimeter cube of aqueous solution. The solution has an osmotic pressure of 5.85 millimeters of mercury at 298 Kelvin. Now you have to tell what is the molar mass of albumin and what is the height of water column placed in solution. You can consider density of water equal to 1 gram per centimeter cube. Now molar mass of albumin can be calculated by using the relationship Ma equal to Wa into St upon pi V. Here Wa equal to 1.08 grams, S is 0.0821 liters atmosphere per Kelvin per mole, absolute temperature equal to 298 Kelvin, osmotic pressure is given in millimeters, you have to convert it in atmospheres by dividing it by 760. Hence, pi will be equal to 5.85 upon 760 atmospheres. Volume is given in milliliters, you have to convert the volume in liters. Therefore, volume will be 50 upon 1000 equal to 0.05 liters. Substituting these values in equation 1, you will get molecular mass of solute equal to 1.08 into 0.0821 multiplied by 298 upon pi, which is equal to 5.85 upon 760 multiplied by volume, which is equal to 0.05. Now molecular mass of solute comes out to be 68655 grams per mole. Coming to the next part of the problem, we have to calculate the height of the water column. You know that osmotic pressure is equal to H into D into G. Putting all these values, we can calculate the height of the solvent column. Pi is equal to 5.85 upon 760 atmospheres. If you want to convert the osmotic pressure from atmospheres to Newton per meter square, you have to multiply it with 1.01325 into 10 to the power 5. Hence, osmotic pressure comes out to be 5.85 upon 760 multiplied by 101,325. This is equal to height in meters, density in kg per meter cube, which is equal to 1 into 10 to the power 3, and g, acceleration due to gravity, which is equal to 9.8 meter per second square. Putting all these values and calculating, you will get the value of h, which is equal to 7.958 into 10 to the power minus 2 meters or 7.958 centimeters. Coming to the next example, calculate osmotic pressure of 5% solution of cane sugar, which is known as sucrose, at 15 degrees Celsius. Here, molecular mass of sucrose is 342, weight of sucrose is taken to be 5 gram, volume is 100 ml, which means 0.1 liters. Putting all these values in equation pi V equal to Wa upon Ma into St, we will get pi equal to 5 upon 342 into 0.0821 into 288 upon 0.1, from which you will get osmotic pressure equal to 3.453 atmospheres. Now we are going to discuss another example related to Wantoff's theory. A solution of cane sugar containing 34.2 grams per liter has an osmotic pressure of 2.4 atmospheres at 20 degrees Celsius. Calculate the value of R, or you can say value of S, in liter atmospheres. From Wantoff's equation, you know that R is equal to pi V upon T. Here V is the volume of the dilute solution in which 1 mole of the solute has been dissolved. On putting the values of osmotic pressure equal to 2.4 atmospheres, volume equal to 342 upon 34.2 equal to 10 liters. Here V is the volume of the solution in which 1 gram mole of the solute has been dissolved. Absolute temperature equal to 20 plus 273 equal to 293 Kelvin. Substituting all these values, we will get R equal to 0.0819 liters atmosphere per Kelvin per mole. There is another example for the practice for you. Experiments shows that 10 grams of cane sugar in 1 into 10 to the power minus 3 meter cube of solution produces an osmotic pressure of 6.68 into 10 to the power 4 newtons per meter square at 273 Kelvin. Calculate the value of R, or you can say value of S, in SI units. On using the equation R equal to pi V upon T, we can calculate the value of R or S. Here also we have taken V equal to volume of the dilute solution in which 1 gram mole of the solute has been dissolved. In this case, pi will be equal to 6.68 into 10 to the power 4 Newton per meter square. V will be equal to 1 into 10 to the power minus 3 into 342 upon 10, which is equal to 3.42 into 10 to the power minus 2 meter cube. Substituting all these values in the equation, we will get R equal to 8.36 joules per mole per Kelvin. We can also calculate the osmotic pressure of a solution which is obtained by mixing two different solutions. We can discuss this with the help of an example. Calculate the osmotic pressure of a solution obtained by mixing 100 ml of 3.4% solution of urea and 100 ml of 1.6% solution of cane sugar. You know that molecular mass of urea is 60 and molecular mass of cane sugar is 342. We can use the relationship pi V is equal to nRT. As we are going to mix two solutions 100 ml each, hence the resultant solution will be equal to 100 plus 100 equal to 200 ml. So, volume in liters will be equal to 200 upon 1000 equal to 0.2 liters. Now, if we use this relationship for the osmotic pressure of urea, pi V is equal to nRT, where n is equal to 3.4 upon 60. Putting all these values in the equation, we will get pi equal to 6.81 atmospheres. This is the osmotic pressure of urea solution. Now, we will calculate the osmotic pressure of cane sugar solution. Here also V will be equal to 200 upon 1000 liters, N will be equal to 1.6 upon 342. Putting all these values in the equation, we will get pi into 200 upon 1000, which is equal to 1.6 upon 342 into 0.0821 into 293. Here osmotic pressure of cane sugar equal to 0.56 atmosphere. According to the Wantoff's theories, dissolved substances behaves like gases. Hence, they must obey Dalton's law of partial pressure. Therefore, the osmotic pressure of the solution obtained by mixing two different solutions will be equal to the sum of osmotic pressure of the two solutions. Therefore, the resultant osmotic pressure will be equal to the osmotic pressure of urea plus the osmotic pressure of cane sugar. Hence, it is equal to 6.81 plus 0.56, which is equal to 7.37 atmospheres. When we talk about concentration of solutions, we must also discuss the concept of activity and activity coefficient. G. N. Lewis discovered that the concentration of ions and molecules gets lowered than their actual concentration in the solution. He said the apparent value of concentration is called activity. Hence, activity can be defined as the effective concentration of a molecule or ion in a solution. And the activity coefficient gamma can be defined as the ratio between the activity denoted by A or effective concentration and actual concentration of the molecule or ion in the solution. Therefore, gamma or coefficient of activity is equal to effective concentration, which is denoted by A, upon actual concentration, which is denoted by C, or we can say molarity. Hence, A is equal to gamma into C, means activity is equal to coefficient of activity into concentration. Concentration can be expressed in terms of molarity also. As coefficient of activity can be determined experimentally, hence we can calculate activity of the solution. Actually, the effective number of cations and anions reduces in the solution because they form ion pairs because of strong electrostatic attractions between them. In this figure, you can see that positive ion and a negative ion form an ion pair. Here also positive ion and negative ion is forming an ion pair. Therefore, overall concentration of the ions reduces. Hence, the apparent concentration or effective concentration reduces, which is known as activity. In the mathematical expressions for Henry's law, Raoult's law, law of mass action or Ostwald's law, the concentration of the species must be replaced by activity for accurate results. We can understand the concept of activity with the help of an example. Calculate the effective concentration of a 0.0992 molar solution of sodium chloride at 25 degrees Celsius, for which activity coefficient is 0.782. Now, we know that A is equal to gamma into C, where A is activity, gamma is coefficient of activity and C is actual concentration. Putting all the values, we can calculate A. Gamma equal to 0.782 and C equal to 0.0992. So, we get A, that is activity, equal to 0.0776 molar. Let us discuss another example related to Wantoff theory. A solution of glycol containing 1.821 grams per liter has an osmotic pressure of 51.8 centimeters of mercury at 10 degrees Celsius. Now, what is the molecular mass of the glycol? As we know that molecular mass is equal to W into RT upon pi V. Here W is the mass of the solute, R is molar gas constant, or we can say molar solution constant, T is absolute temperature, pi is osmotic pressure and V is the total volume of the dilute solution. W is equal to 1.821 grams, R equal to 0.0821 liter atmosphere per mole per Kelvin. Temperature in Kelvin will be equal to 10 plus 273 equal to 283 Kelvin. Osmotic pressure has to be taken in atmospheres, hence it will be equal to 51.8 upon 76. Volume is equal to 1 liter. Putting all these values in the equation, we will get molecular mass of the glycol equal to 62.07. Let us revise what we have discussed today. First, we have deduced a relationship between osmotic pressure and vapor pressure. Here we showed that osmotic pressure is directly proportional to lowering in vapor pressure, and it is also directly proportional to relative lowering in vapor pressure. Next, we discussed about Wantoff theory of dilute solution, in which we have discussed three laws: Boyles Wantoff Law, Charles Wantoff Law and Avogadro's Wantoff Law. Next, we discussed some examples related to Wantoff theory for better understanding of Wantoff Law. Concept of activity and activity coefficient we discussed in last. In next lecture, we will discuss Wantoff factor and abnormal molecular masses of the solutes which associate or dissociate in dilute solutions.